All right, so we got 10.2b today. In example 1, a particle moves in the plane so two-dimensional movement instead of one-dimensional movement. So in the classic calculus problem, in the classic calculus 1 problem, there's a particle moving back and forth on a number line. This is the classic calculus 2 problem, where there's a particle moving around on an xy plane. So a particle moves in the plane with velocity vector v of t equals t minus 3 pi times the cosine of pi t, comma 2t minus pi times the sine of pi t. So there's the velocity vector. And it's not surprising that it's got two components to it, right? Because in two-dimensional calculus, you need an x and a y for the velocity. In one dimension, you just need a number for the velocity, like positive 5 or negative 3. Now, there still sort of is two aspects even there, right? Because the negative 3 means speed of 3 in the negative direction. So it's still kind of a vector, still has a magnitude and a direction, even in the one-dimensional case. But in the two-dimensional case, you definitely need something, comma something, to express the two components of the velocity vector. Okay, then additional information is that at t equals 0, the particle is at the point (1, 5). So we're just being told one location of the particle at one time. But we don't know all the locations. We just know all the velocities. Okay, so the first question is going to be find the position at t equals 4. So how are we going to figure out the position? Take the antiderivative, right? They gave us the velocity, so we could take the antiderivative. Now there's two ways to take the antiderivative. You can think it through, right? Or you can slap an integral sign on it. So I'm going to slap an integral sign on this to take the antiderivative, just because that's the snazzier method. It wouldn't matter which you did, but I'm going to slap an integral sign on this. Okay, so if I take the integral from a to x underneath t minus 3 pi cosine of pi t, so this is the antiderivative of the x velocity, meaning the x component of the velocity. And I can pick any number I want for a, and then from that a, that'll help me figure out what the c is. So the most convenient thing for a would be t equals 0, right? Because these are times, because it's dt. So they gave me information when t was 0, so I'll put a 0 down there. And then I know that if I put a 0 in to this formula, it's supposed to spit out 1, right? because the x answer for the position at 0 is 1. And this is the x velocity. So, and the input is right there. So I know if I put a 1 in, or sorry, a 0 in to this, it's supposed to spit out 1. And the reason I know that is at time t equals 0, the position for the x component is 1. So then that tells me c is 1, right? So now I have a solid equation for the position, at least for the x component of the position, right? It's the integral from 0 to x underneath this. Just figured out c is 1, so I guess I'll write it down. A little bit of awkwardness in the notation, right? This x is a t. It's a time. This x literally means the x value of the velocity. So I'm not super happy about the double use of x there, but I think you can deal with it. Okay, so then to find the position at t equals 4, I would just plug a 4 into this, right? So I'd integrate from 0 to 4. And again, if we wanted to, we could do this by hand. But we'll just go calculator active today and math 9 this from 0 to 4. Now, before I do that, I want to point out, look at this. This is the integral from 0 to 4 of the velocity, right? What do you get when you integrate velocity from A to B? There's a fancy term for it. Displacement, right? If you integrate velocity, you get displacement. So this is the x displacement plus the original x location. So that's going to give me the final x position. Now I'm not talking about a fare, right? I'm not talking about an x position. I'm talking about the x position. You with me? Okay, so this is the x displacement. Then I add 1 and I get the final x position. So I plug that in. So when I integrated this, I got 8, and then the 8 plus 1 comes out to 9. So the x-coordinate of the position at time t equals 4 is going to be 9. Okay, so I also need to find the y-coordinate of the position. So I'm going to find the y displacement. So that's the y velocity, the y component of the velocity vector. So if I integrate that from 0 to 4, that'll give me the y displacement. And then if I add in the original y coordinate, then I'll have the final y position. So this time I kind of took a shortcut, right? It wasn't super necessary to write out this entire formula, because it didn't ask for a formula for the position. But on a different question, they might ask for a formula, so you could do that. So that comes out to 21. So then at t equals 4, the position is 9, 21. So the particle started at time t equals 0 at 1, 5. And then 3 seconds or 4 seconds later, it was at 9:21. So now we know 2 locations. We know that it was at 1:05, and later it was at 9:21. So we're starting to get a picture of what this particle is doing as it travels on the xy plane. Okay, now for part B, we're going to find the velocity at t equal 4. The next question is find the velocity at t equals 4. This is going to be significantly easier, right? Because they gave us the velocity vector at the very start. So in order to find the velocity at t equals 4, all I have to do is plug the 4 into that formula that they gave me. So it's 4 minus 3 pi times the cosine of 4 pi. I'm just plugging 4 in for t. And then 8 minus pi times the sine of 4 pi. So just put a 4 here, a 4 there, a 4 here, and a 4 there. So I think I can do this in my head. 4 pi is 2 times all the way around, right? So it's the same as 0. So the cosine of 4 pi is 1. So that's 3 pi times 1. So this comes out to 4 minus 3 pi. And then the sine of 0 is 0. So this is 8 minus 0, which is 8. So the velocity, that's the answer to the velocity. Now the one awkward thing about this is we think velocity should be a number, right? Because we're so used to the one-dimensional case. But in the two-dimensional case, the velocity is not a number, it's a vector. So when it asks for the velocity or the acceleration or the position, you need 2 numbers to express that, right? When you're in two-dimensional space. If you're in three-dimensional space, you'd need 3 numbers to express the position and the velocity and the acceleration. But we're not in Calc 3 yet, we're just doing Calc 2, so we're not going there yet. But it would be an easy jump, right? At least with these problems. Okay, so that's the answer to B. And part C says, find the magnitude and direction of the velocity at t equals 4. So it's nice when you have a vector that's x comma y, because it's easier to do the math often. Like if you're going to add two vectors, it's really easy to add this vector to another vector. You just add the two x's and add the two y's, right? So that's why in math class sometimes we really like vectors to be expressed in x comma y form. But it's kind of unsatisfying to express it in this form, because velocity, if you tell somebody, well, what's the velocity, and you say 4 minus 3 pi comma 8, we can't really get a handle on what that exactly means. So sometimes it's better to express it using the magnitude and the direction. It's still the same vector, it's just expressing it in a different way. So what we mean is we're going to say where the velocity is. Is it going this way or this way or this way, the direction, and then the magnitude is how much oomph it has, the length of it, right? Okay, so first of all, let's go with the magnitude. How do you find the magnitude of a vector? It's Pythagorean theorem, right? Okay, so I'm going to write this. It's going to look a little awkward to you, but it's legal to write that. They look like absolute value signs, but they're actually magnitude signs. So these two things mean find the magnitude. And yeah, that's exactly right. The magnitude is the length of it. So you take 4 minus 3 pi squared plus 8 squared to figure that out. So just so you have a picture of what's happening, we've got, well, this is about 9. So this is about negative 5. So the vector is about negative 5, 8. And what we're doing right now is we're finding the magnitude of it, the length of this vector. So let me just type that in real quick, get a decimal for it. It's 9.666. So when you take the magnitude of the velocity, what concept are you getting? Let's go back to the one-dimensional case. Let's say you take the absolute value, let's say the velocity is negative 4, and you take the absolute value of that and get 4. What is that telling you? The speed is 4, right? So it's the same thing in the two-dimensional case. This magnitude of velocity is the speed. And then we also need to find the direction of it, right? The direction is whatever this angle is. So now we're going to try to find that angle. So the way we're going to find that angle is we're going to look at this triangle. That's 4 minus 3 pi and 8, right? And we're going to do the inverse tangent of the 8 over 4 minus 3 pi. I'm getting negative 0.975. Okay, that's a little bit awkward because that's not right. Right? A negative angle goes this way. So what's going on is there's another vector that's positive 5 and negative 8, right? That would have the same inverse tangent. See, the calculator doesn't know which of these numbers is negative. It just knows that overall it's negative. So it didn't know whether the top number should be negative or the bottom number should be negative. So it gives the answer that's in the first or second quadrant, not the answer that's in the, sorry, it gives the answer that's in the fourth or fourth quadrant, not the answer that's in the second quadrant. We know it's in the second quadrant because we know that the 4 minus 3 pi is the negative answer. So we have to convert this into a second quadrant angle. Okay, but the reference angle, 0.975, is the same in both cases, right? This reference angle is 0.975. So this reference angle is 0.975. So if we just take pi minus that 0.975, then that'll give us this angle, right? So completely without rounding, it's pi minus the inverse tangent of 8 minus, I got to be careful because this needs to be positive, so. So that angle is 4.117. So that tells you the direction that the vector is traveling in. It tells you that the velocity is in the direction of 4.117 radians. Okay, so now connecting back to this picture, I don't know what this path looks like, but I do know that maybe it's something like this. And right at that moment, when t equals 4, it's traveling in this direction, right? The 4.117 direction. And it's traveling with a speed of 9.66 meters per second. So this vector here is showing me the velocity on the path. So if this is a car, then the 4.117 is where the headlights are shining, right? It's the direction that it's going in right then. And the 9.666 is how fast it's going. If you're in a car, you look down at the speedometer, and that's what it says, 9.666. Right at that moment. Now, a split second later, it's in a different direction. And a different speed, maybe, right? This is the instantaneous direction and the instantaneous speed, right at t equals 4. Okay, so now we're going to find, so this is part D, I guess. So we're going to find dy dx. So when you're in 2 dimensions, how do you find dy dx? What's the formula? dy dt over dx dt, right? The second derivative is significantly harder, right? It's not what you think it should be. It's the second derivative over the dx dt still. So, but anyway, this one's easy. It's just dy dt over dx dt. And in this case, they gave us the dy dt right at the start of the problem, right? It was this. So the formula is 2t minus pi times the sine of pi t all over whatever that other formula was. Oh, it's right there. I didn't erase it. Cool. So t minus 3 pi cosine of pi t. Just make sure you get the y component on top and the x component on the bottom. And then at t equals 4, we've already done it, right? It's 8 over 4 minus 3 pi. So this is another way to express the direction of travel, right? So here's the particle, and it's traveling in the up 8 over 4 minus 3 pi direction. So dy dx is the direction of travel. Now, a lot of times we like to have that in the form of an angle, so we take the inverse tangent of it to get the angle. But you wouldn't have to do that to express the direction. The direction can be expressed by a slope, up and over. Okay, so that messes with people because in the two-dimensional case, dy dx is the direction that it's moving in. But what is dy dx in the one-dimensional case? It's the velocity, right? And when you have time down here and position here, then slope is meters per second. So we have that ingrained so heavily in our brains because we did the one-dimensional case for 6 months that you're going to accidentally think that dy dx is the velocity. But it's not. In this case, dy dx is the direction of travel. Because the graph isn't time and position. The graph is position and position, right? So the slope is not velocity in that case. It is the direction of the velocity or the direction of travel. So now we're going to find the total distance traveled on the time interval 0, 4. So in the one-dimensional case, how do you find total distance traveled? Absolute value of velocity, and then integrate that, right? It's the same exact formula in the two-dimensional case. The only thing is, in the two-dimensional case, we're not allowed to call these bars absolute value. We call them magnitude. So notice that for part A, we did this, the displacement. And now we're finding total distance, so we're doing this. Okay, and when we take the magnitude of the velocity, isn't that the Pythagorean theorem? That squared plus that squared, right? And I got to integrate that from 0 to 4. What's another way to think of the absolute value of the velocity? What's the terminology for that? Or magnitude of the velocity, that's speed. So we're integrating speed here because we don't want any of the negative velocities or any of the 45-degree angle velocities to cancel out with any of the other 45-degree angle velocities, right? We want them all to be speed so that we're adding up all the little speeds times time to get total distance. This little speed times time, this little speed times time, speed times time to get total distance. Same thing in the one-dimensional case. You're taking the absolute value of the velocity because that's speed. If you integrate speed, you get total distance traveled. Okay, now before we type this in, I want to think of this. What is this? This is dy dt, isn't it? Let me write it up here. dy dt, dx dt, right? So another way to think about this is we're integrating the square root of dy dt squared plus the square root plus dx dt squared. This is this, right? But what is this a formula for? Arc length, right? Well, in this case, isn't the length of the arc the distance traveled? So that's another way to think about it. Of course, if you're taking the length of the path, that's the distance traveled. So the integral of the speed is distance traveled. The length of the path is distance traveled. However you look at it, it comes out to 33.533, I think. Yes. And if you have a question like this on the AP test, type it in, press enter, and then read the next question. Because it takes literally 30 or 45 seconds for the TI calculators to get this 33.533. So don't sit there and watch the thing spinning. Read the next question, and then when the answer pops up, write it down, and then you'll get your extra minute or so to think. Okay, I think that's it. Let me double check. Yeah, everybody doing okay?